Let's start our discussion of systems of equations with a geometric formulation. The idea is that if I have two linear equations and I want them to be satisfied simultaneously, I can think of this as drawing two lines in the Cartesian plane and looking for their intersection. As long as they're not parallel, I'll have a solution. And as long as they're not the same line, I'll have exactly one solution. So the picture might be like this. I might have one line as y equals m1x plus b1, and I want that to be true. Well, that's true infinitely often. It's true as long as you live on this line. But then I also want y to be equal to m2x plus b2. So I also want to be on this one. That happens exactly at one point, that intersection. Our goal is to find that intersection. So to write this in sort of a notation you might see on the CLEP exam, I want to have y equals m1x plus b1. So this is equation 1. And then y also equal m2x plus b2. So this is equation 2. The fact that I want to have these both be satisfied at the same time, simultaneously, is why we call this a system of equations. There's two of them that work together to give me a unique solution. So how do we do this? Well, the idea, I think, is actually straightforward. I know that y has to be equal to something from the first equation, and y also has to be equal to something from the second equation. So I can set those two formulations of y equal to each other. And then I'll just be able to solve for x. So the idea is that I have equation 1 and equation 2. And I want to set these equal. So I have minus 3x plus 4 should be equal to 4x minus 7. And then I'll just solve this. So let's say that 4 minus 7 is equal to 4x minus 3x. So 11 is equal to 7x. So x is equal to 11 divided by 7. So this tells me that where these lines intersect has x coordinate equal to 11 over 7. But I also want to know the y coordinate. I've only sort of told you half of the story here. I only told you where they intersect with respect to the x-axis, not what the y coordinate is. But that's easy to do. I just plug in x into either equation. Y either one, well, I know they're equal here. If I didn't know that, they would each give different answers. But because this is the point of intersection, it doesn't matter which one I plug into. So I know y is equal to, say, 4 times 11 over 7 minus 7. So 44 over 7 minus 7, and I suppose we could get a common denominator here. 44 minus 49 over 7. So this is like minus 5 over 7. Okay. And we can check, in fact, that it didn't matter which one I plugged into. Let's look at what happens if I plug it into the first one. Y equals negative 3 times 11 over 7 plus 4. So negative 33 over 7 plus 4. Again, I find a common denominator. So 4 times 7 is 28 over 7. So again, I get minus 5 over 7. So they're in agreement, which only happens if I did the first part correctly, because I had to find the point of intersection. So in that case, it doesn't matter which one I plug into. Both work. Now, we can look at more complicated examples where I don't just have two linear equations, where I have maybe a linear equation and also a quadratic. So how can I do this? Well, the same idea works. I have two formulations for y. Y equals some linear function, and y also equals some quadratic function. I can set those equal and solve. What's the difference? Well, the difference is, at the end of the day, I have to solve a quadratic function, not just a linear function like I did before. So let's just sketch out how one would do this. So I would say that 3x plus 4 from the first equation is equal to x squared plus x plus 1 from the second equation. So I set this equal to 0, and I get x squared minus 2x minus 3 is equal to 0. And I ask myself, do I know how to solve this? Right? The technique would be no good if I got to a point that was useless. But it's not useless. I know how to solve this equation. Given any quadratic, I can always use the quadratic formula. In this case, I think it's actually even simpler. This factors nicely as x minus 3 and x plus 1, so that x is equal to minus 1 and 3. So let's check this. Plug in minus 1 into 3x plus 4, and I get 1. Plug minus 1 into the bottom, I also get 1. Plug in 3 on the top, I get 13, and on the bottom, I also get 13. Okay, so in this case, the same kind of substitution method worked very nicely. It did require me to solve a quadratic equation. So that's how it gets more complicated. Now, of course, we've talked about looking at systems of equations. We can also look at systems of inequalities. So just replace those equal signs with inequalities. So how does this change things? Well, I think it's helpful if you think of it geometrically. Each of the equations is going to have a half-plane solution. So I need the intersections of those half planes to be where my solution is. So I always like to plot these before I try to solve them analytically. So let's look. Here I have that was terrible. I have the inequality minus 2x plus 1 should be less than or equal to y, and x plus 2 should be less than or equal to y. So let's plot y equals negative 2x plus 1. I'll do that in green. Okay, so here is y equals negative 2x plus 1. And I want that to be less than or equal to y. And then I'll also plot y equals x plus 2. So I see where the lines intersect, but I want to look at the inequalities now. So when is minus 2x plus 1 less than or equal to y? Well, I've already drawn that line. So then this will be true in this region, right? So let's pick a point and check. So for the first one, let's try 0, 0. Is it true that 1 is less than or equal to 0? The answer is no. So 0, 0 is not in that solution set. So it'll be on this side of the line. And then for the purple one, we'll also check, is 0, 0 in the solution set? Well, is 2 less than or equal to 0? No. So I'm on this side of the line. So this checking a point thing just tells you which side of the line you're on. All right, so now I have a picture of when each inequality is satisfied. So when are they both satisfied? Well, it's the overlap of the purple and the green. So it's this upper quadrant here. So I'm going to box it in blue. So here and here. Because this is the part where both inequalities are satisfied. So I think it's very helpful to think in this geometric way. A common question on the CLEP is to show you an inequality system and to say identify which of the following plots shows the region of solution. So this type of example is potentially very important.